All right. 12:10 or so. I imagine we'll still have a handful of people coming in and everything else. Granted, I do expect us to be a little bit lower than normal because we just came out of an exam. And what an exam it was. I think we're going to spend the first little while here talking about that. The slides and everything else. Let's chat about some of the stuff that goes into the exam. So, all in all, let me set this thing properly. Exam 2. A couple interesting facts. Exam 2 average score was sitting right around 56% when all is said and done. So the way that I think I'm gonna, let me finish writing this out. Average time, for example, so that's average score. Average time is somewhere right around 81 minutes. So one of the things that I wanted to do here, of course, I can start by saying this average is quite a bit lower than I expected to see, realistically. And I'm coming into this a little bit more somber than my usual bright and cheery self. Because I imagine that probably does not mesh well with having a discussion about an exam that I would imagine many of you found very, very difficult. But I think the way that I want to run this, I do want to chat about this. So I want to get some opinions on this. I do want to share my thoughts first, though, just because it might address some points that you guys might try to, make here or anything else. So one of the things that I do want to start with on this one is, I did expect this exam to be harder. I did expect this average to be lower. Generally speaking, when I'm talking about exam averages in this course and everything else, I would have been fairly happy somewhere around 65%. And I know that sounds incredibly low, but that takes into account there are low grades that come into this and everything else. There are always a number of low grades on the exam. When all is said and done between the distribution of everyone, despite the fact, we've got scores kind of all over the place, a 65% average to me feels like right around the sweet spot. That usually implies to me that the difficulty was scaled pretty well. It was not a gimme kind of easy or anything else like that. Everything ended up meshing pretty well. So this is quite a bit lower than that, right? Of course. And I realize that, and I don't want to remove from the gravity or anything else, recognizing that I have this part in anxiety and stress that you feel towards the exam, towards the course grades in general. I realize that is essentially what I do at that point. I felt myself going through the exam. I go through a process where, as I'm writing the questions, I solve the questions out. I think about the solutions. I pass it off to other people to give me opinions on the exam, on that one, their take on the exam. And of course, when the exam is all said and done, we take it a few times and get a sense for how long we expect the exam to take. Going into this exam, nothing felt off surrounding that. From the time it took and everything else, from my perspective, everything felt right on that one. The average time is, kind of right around where I would expect it to be as well with that. But for the scores that we had, I found the average time spent on the exam perhaps a bit low. And I say that because there were a few people that were taking this more out. Actually, I even overestimated this. I think some more numbers have come in here. Average time is more like 76. And apparently I'm writing on the background because now we just don't have texture there. How did that happen? But anyways, the average time felt low for the scores that we saw. I'm not entirely sure on that one. I have been thinking through this ever since I have been seeing these scores. If you had emailed me and I took a little while to respond, I have been thinking about these numbers a lot over the last 24 hours. And so I've been just thinking through a lot of what I have wanted to say. Unfortunately, I'm kind of short here. Um, I don't know that I have good words. But that's kind of my perspective on this thing so far. But I would like to. I think we've got enough people here that I can get a pretty good sense of the population of the course. Um, let's talk about some things in order here. How did we feel about the exam as a whole? Let me just get a sense on that one. You can throw opinions up. Probably in chat is the easiest thing because we've got enough people. Not goo really hard. Okay. 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 I see time is a big theme here. And that is a little bit rough. Okay. Interesting. Okay. So, kind of along the same lines with that, how did the questions on the exam feel compared to, let's say, the homework questions? Interesting. Interesting. So, one point that I do want to highlight on that one. One comment that I'm kind of picking out from all of this stuff. The idea that you have not seen the problems before is, I mean, in a sense, expected. One thing that I do want to address with that one is that there's a difference between a course like this and a course of physics that you would have seen in high school, for example. Um, the part that I know of this is largely that I have done tutoring for both. I have worked with both sets of material. Um, the theme towards a college physics course, and especially the exams being online and as they are currently, is that the problems that you see are more than likely problems that you have never seen before. And that is to be expected. That is designed that way. That is not something necessarily that is wrong with it. Our goal is that you can see a brand new problem that you have never seen before and still pick your way through that. Not to like your feelings and everything. I do not want to diminish from that. I understand where you're coming from with that one. I have seen some similar things before in my own time. You know, in my student hat, I can appreciate that comment very much. In my professor hat, I do want to give a warning there of I'm trying to not introduce new concepts per se, but to see old concepts perhaps revitalized is an important one. But I get the sense a lot of people, I don't think I have seen only a handful of comments that the exam questions were of comparative difficulty. I think most people feel that they were much more difficult. I'm just going to store that in Thought Bank for now. One of the things to that effect is I am working on getting these solutions written out and published to you guys by tonight. I've got most of them written out already. Currently working on question 14 of 18. So I plan to have all of these things out to you guys tonight so that we can discuss these in a little bit more detail, kind of on a level playing field for this. Um, and I see time as a common theme. Time seems to be one of the biggest themes in this one. Normally, it is my intention that you guys will have plenty of time to finish through this one. And that is an interesting kind of, in contrast to what I'm seeing from average time spent on the exam here. I do think that is kind of an interesting take, and I'm very glad that you guys are sharing this one with me, because it is certainly, like, I have seen some of those times and everything else, of course. I'm looking at, I've got on a student by student how long you have spent looking at a question, how long you spent on the exam as a whole, all of those details kind of right in front of me here. Averages are just a good way to sum up everything. But of course, looking at some of these things. Yeah, going through it twice like that. I'm trying to think if there are. Okay, let me write these down then before I forget. Thoughts. Questions more difficult than homework. Questions. Not enough time. How do I want to write that? That seems like a very common theme here as well. I'm going to put this as, let's put this as a little square dot. A lot of backtracking. Let's move that one slightly over. We'll put that as a an underpoint. Man, this background thing is going to kill me. Yeah, and I will kind of doubling up on the 6 multiple choice questions. I realize does make it more difficult to guess. It is my compromise with going to online multiple choice questions without Proctorio or anything else with that. I very much do not want to use Proctorio, right? I have already heard enough cases of different people being in different circumstances. Of Proctorio would be the worst thing in the world. I recognize that immediately on its face that Proctorio is not the way to go with a lot of these things. That being said, because we are doing this online, because there is a certain degree of freedom associated with all of this, the number of Yeah, I do not want to see Proctorio in this course. I don't want to see any sort of proctoring service like that or anything else in this course. 6 multiple choice questions is to try and cut down on some of those other things that may be associated with the amount of freedom that comes with it. And in addition to that, it is also a strict goal of mine that for there being 6 multiple choice questions, I try not to have any what I'll call pitfall answers. Pitfall answers being if you had solved the question an incorrect way, it would have given you this answer instead. I try very hard to not have any of those. Anytime it shows up, anytime that anything like that would show up, that if you solved it the wrong way and found an answer among them, it is purely circumstantial. It is an unfortunate combination of numbers. So that is my goal in all of this, to try to make it in such a way that you know when you've got the right answer, right? That's kind of the balance that I'm trying to strike with all of this, so that guessing and comparing answers or anything else is more difficult than it's worth, but that you've got some validation when you know you're on the right track. Still no Bractorio or anything else, though, because this is the format of the exam that we have ended up working out, since at this point I've been teaching online more than I have in person. This is the system of exam that we have found to work pretty well for us. You know, myself and my colleagues as well, going through the course with this one. Hello? Okay. Sometimes if you notice that sudden dark spot, sometimes one of my monitors just decides to cut out for a little while. I don't know why. Okay. I'm trying to think. Let's go with this. Do we have yeah, and in addition to that, we don't have typical mastering questions because oh boy. Right? I know there's enough gripe already with the mastering homework questions as is. You know, that's part of the reason why I give you guys 10 attempts on this. It is not the only reason, but part of the reason that you get 10 attempts on the homework itself is because sometimes there's just some nonsense with putting those answers in the first place. On a rare occasion, they round in a weird place or something else like that, or the answer is just a little bit strange. So we try to avoid that as well. Right, we try to avoid deductions because of that. But that's why we are sticking with multiple choice as well. I have tried to include some of those free response answers before, and they do not go over well. Okay. So time-wise and everything else, my goal here, let me talk about some things that immediate thoughts that I've got on this. I'm not going to extend the time of the exam. And that is, let me finish the thought before we think about that too much more or anything else. I do not want this to take more than 2 hours, right? I want you to have enough time to finish the exam within 2 hours. If you're in a 400 level course and we're doing some sort of take-home exam, maybe that lasts a little bit longer. I have taken some exams that I have spent on the order of 20 hours on, but that is not this course. This is a timed exam, and being a timed exam, I do not want to see this go on for any longer than 2 hours. You know, that's our limit right there. I think, though, that there is going to be a bit of reevaluation in the timing of things. Again, I do not come into this with the sense that I am just going to beat you with the bat with nails in it that is physics. Right? I plan for there to be, you know, some degree of difficulty at these exams, realistically. There are going to be some questions that are on the order of the harder homework problems. There are going to be some questions that are on the order of the whiteboard problems. Yeah, and I'm getting that sense here that it's not anything to do with more time might have helped a bit, but it's more of a symptom rather than the cause. I don't want to say that it's supposed to be a hard class. That's a tricky spot to say. I know it's a hard class. Um, I think it is a hard class, more of a matter of circumstance. And this is going to be, Anthony's hot take. It's a lot of material. It's a whole lot of material, and it's not easy material. I don't necessarily want to say, like, the material itself can be hard. The course is not necessarily designed to be hard. The course is circumstantially hard because it's a 5 credit hour course being shoved into a single semester. You guys have other things going on, and there's a lot of material to cover. There's a lot of work to be done, and we don't have the time to sit on topics for perhaps as long as I would normally like to. There are going to be some of these topics, like once we hit chapter 12, we're going to spend a good 4 lectures on chapter 12, right? There are certain things that we do emphasize a little bit more, certain things that we have planned to sit on a little bit longer. But in other circumstances, you might expect this course to be a much longer course given how much material is actually covered. Right. The fact of the matter is that you guys all have other things to do while you're in college, so we can't spend a full year working on this material and a full year working on Physics 192. You guys got to have this stuff now so you can keep moving on. I don't have a better solution on that one. That's the thing that we need to take up more with academia on that. So I think what that stems from, though, given the circumstance that we are in, the course is hard because of the time constraints surrounding the course as a whole. The exams are going to be kind of representative of that, of how much material we've had to cover and how little time that we have had to cover it. But my takeaway so far, and I'm going to do this in the second lecture as well, so I want to try and get as many opinions on this as possible. My takeaway here is that the questions were a little bit more difficult than we had expected. My takeaway is that, especially with that, but kind of as a result of that, the not enough time, I'm not taking that as increase the amount of time, but because the questions were more difficult, because there's a lot of backtracking, it sounds like, we ultimately felt like there wasn't enough time for all the work that we were trying to do. Do we have more thoughts on this one right now, whether it be the course, whether it be the exams, whether it be anything else? If it's on your mind, hit me with it. Lowest exam score is indeed dropped. Right? Not counting the final. The final is its own separate thing because it's cumulative. But of the 3 midterms, the lowest exam score is indeed dropped. Extra credit assignments, those do show up in mastering. Generally speaking, I try not to touch the exams too much. Largely speaking, because we have the exam dropping policy and everything else, I usually try to leave those in place and not adjust those scores too much. Well, no, I'm not going to ask that. Never mind. Okay. So I am thinking about this, though. I did want to let you guys know that, and I did want to give a chance for you guys to kind of voice opinions on this and everything else. I recognize that this ended up being harder than intended on this one. So, I've certainly got some thoughts about that and everything else. Yeah, it's kind of consumed all of my thoughts recently. So thinking about what I have wanted to say here, thinking about how I wanted to present all of this. I don't like to see averages like this. I know there are some people that love to see bell curves come out of their grades. I am not one of those people. I disagree with the bell curve for, well, at least this material. Maybe there are some circumstances where I could agree and see in a bell curve somewhere, but I'm not a big fan of bell curve assignments. Doesn't feel good to me. Okay. If you do have more thoughts, of course, you are more than welcome to send me an email. I know I have chatted with plenty of people already surrounding a lot of these things. However you want to talk about this, I really am more than happy to chat about all these things. All of that stuff I think is good to have some good discussion here and everything else, to understand what's going on, to think about what we can do preparing and everything else, your end, my end, all of that good stuff, looking towards what we can do with these. I think we're going to open up this discussion again, probably not Friday, but perhaps Monday. We'll chat about this a little bit more. We'll let the dust settle a little bit. I'll have the solutions out. You'll have the chance to look over those. We can chat about some of these things a little bit more then. I think, with a little bit more of a retrospective aspect on it, I think that'll be a good time to have some more discussion. So let's plan on talking about this again on Monday. Let's look towards the future a little bit more, discuss what goes into that, and we can come up with some good solutions here to everything surrounding this. Any last parting thoughts or anything else right now? Okay. So if you change your mind on that, or you don't want to talk about it in a public forum like this, you are, of course, more than welcome to send that to me in an email. Again, I'm always happy to chat with you guys. I do recommend, if you're going to be using resources and everything else, please take advantage of the fact we have my TAs are scheduled out so that they are commonly available kind of all over the place. I don't have a ton of office hours or anything else, but we have office hours scattered throughout every day, excluding weekends. But if it's on weekends, send me an email. I'm happy to respond to that stuff. Please, they are literally being paid to help you guys out with these things. They are scheduled for that. That is what they get paid for. So, don't be afraid of chatting with them, having them help you work through problems or concepts or anything else. That includes myself. I'm including myself in that one. Please come to office hours, chat with me, keep open lines of communication, right? All of these things. I have not been getting nearly as many emails or nearly as many people in my office hours as I have been expecting to. Sometimes I know my writing comes off a little bit short. Oftentimes it's because I'm responding from my phone very quickly. And if I'm on my computer, I'll put a little bit more preamble and everything else, just because it's faster typing. But I have a problem with tons of typos when I'm typing on my phone. So I try to keep things short to avoid those. It is, I really am, I'm opening this up right now, even if it sounds like I am just kind of getting right to the point or anything else. I really do look forward to all of your emails. I look forward to being able to help you guys with things. I am always open for your questions. So, with all of that being said, let's close that box for now. Let's open that one back up in a little bit here. If we are not planning on chatting about it anytime sooner, we'll talk about this again on Monday. A little bit more discussion. For now, there is no rest for the wicked, unfortunately. We are going to take it a little bit easier today, but we do still have some things to talk about because, again, this course moves like a freight train. So, we have seen this picture before. This picture being what we had seen when we first started talking about energy. We said, hey, there is a combination of problems. The kinematics and forces have a very tough time of solving. It's possible, but it's difficult. If we, for example, take our flat slope and we turn it into a curved slope, just like what we've got up here, right? This is not something that's very easy for forces to deal with. Because in this case, our forces are constantly changing direction. And unless we can come up with a very clean expression of exactly how those forces are changing direction at all moments in time, this is going to be nearly impossible to solve. So instead, we said, all right, well, perhaps there's another way to do this, and that other way that we discovered was energy. In fact, one of our kinematic equations had been derived from energy in the first place. We just hadn't talked about it like that. Our VF squared equation comes from a change of kinetic energy because of work being done. Anytime we've got that force, extended to the acceleration, and some distance that it covers, that is work to be done. So really, that last kinematic equation was already a work in kinetic energy theorem usage, whether or not we realized it at the time. But there was a second set of problems that we said was also something that was very difficult for kinematics to describe, and that was collisions. The big thing that we have been avoiding this entire time, anytime we're talking about kinematics and projectile motion, is that when the object hits the ground, all bets off. We stop looking there. We look right before it hits the ground, because that's where kinematics still applies. Once it hits the ground, it is exerting some force on the ground. The ground is exerting some force on it. We have different things going into collision like sound and heat and vibrations and the breaking of atomic bonds, and all of those things together are very, very difficult for us to model with kinematics. Again, we run into this issue where suddenly we have forces acting and they're non-time constant forces. Right? We don't have any sort of time constant thing. We don't have a very clean expression. But today is the day we start to look at some of this, how we understand many of these types of problems. And that being momentum. You have probably heard of momentum before. We talked about it even a little bit when we were talking about like the water bucket swinging around, right? It's the difference between a car and a train, right? Especially if you've been driving into Oxford or anything else like that, you might have been just lucky enough to drive alongside the train. As it turns out, the train goes right around the same speed of a car across the tracks, right around 50 miles per hour, 55 miles per hour. We've got a bunch of curves on our road where the train is kind of a straightaway the entire time, so we about keep pace if you're going the speed limit. But realistically, let's imagine you're in another car. Which one do you want to be hit by? Ideally, you don't want to be hit by either one, but if you had to be hit by one, which one would you rather be hit by? Probably a car. I'd agree with that, right? An accident with a car doesn't make any of... the accident with the car doesn't make the YouTube compilations, right? It doesn't show up on news stories or anything else because for the most part, two things of relatively equal mass, especially if it's a smart car, right? If it's a smart car, maybe you'll just blast through it. But realistically, the difference between those two is the momentum behind them, right? The train has much more mass. There's a lot more going into it. If we look at it purely kind of from the forces perspective, it's back to our description of the truck versus the mosquito. Technically speaking, it's the same force going both ways. Train hits car, car hits train. Same force in both directions. The difference is the train's mass. And the other side of that is thinking about the train's momentum versus the car's momentum. We've gotten a little bit darker than I intended that question to go. So let's reel it back here for a minute. But how do we actually define momentum? Of course, I'm already kind of leading into a lot of these things. Of course, a big part of it is the mass. More momentum, generally speaking, means more mass. The train has more momentum, not because it's moving at a different speed, because it has much, much more mass. Oh yeah, I remember that train derailing. That was very obnoxious for a little while. It was one of the only times that I was actually going out of my house and suddenly everything was blocked up. But the other part of that, of course, is momentum. Right? Realistically, if you get hit by a train moving at 1/4 mile per hour, which is still moving, you're probably going to be like, ow, that might have bruised my hip. Right? You're probably not going to be run over by a train or anything else at that point because, realistically speaking, that impact is going to be very light. You're going to feel a sudden jolt, of course, but it has much less momentum because it has much less speed. So those are the two things that momentum depends on. Mass and velocity. And of course, being that we're dealing with velocity and not just speed, there is a magnitude of momentum that is based on speed. But generally speaking, we're going to treat it as if it has these two components as well, right? If velocity has an x and y component, so too does momentum have an x and y component. That is to say, momentum is another vector. And it always points just in the exact same direction as our velocity. So that's nice and easy. If the object is moving upwards, the momentum is pointing upwards, right? They always match together. So how does this compare to some of our older things? Well, let's take a look here. Let's take Newton's second law, and let's, call acceleration by its full name, or maybe not its full name, but its like middle name. Acceleration, technically speaking, is the rate of change of velocity. So if we plug that expression into our Newton's second law, F is equal to ma, what we end up getting is this expression right here. F is equal to mass times the rate of change of velocity. We haven't done anything crazy yet. This is just plugging in the definition of acceleration. What if instead we had just go ahead and move that mass into the derivative? That's not a big deal, actually. We can do that pretty freely, because as long as we don't see any sort of change to the mass, that works perfectly fine. Right? If the mass is not changing, then of course there shouldn't be any problem moving it within or without that derivative. If it had been a constant on the inside when we took that derivative in the first place, then we could have freely pulled it out. Then I feel totally comfortable freely moving it back in as well. Now, if we look at what we've got right there, mv, that is our expression for momentum. That is to say, force is our change of momentum. It's the rate of change of momentum. So, for any of these things that we would have moving, of course, the momentum of a block that looked like this, colliding with some other object, there is going to be a force for some amount of time, and then when we look in the final picture, it has a different momentum than what it had in the first place, because there was a force acting for some time on that object. A force over some time creates a change of momentum. So, that change of momentum is what we refer to as impulse, right? So this is not just anything else. If you've got a lot of impulse, you've got a lot of change of momentum. Take that however you want to, whatever way matches very well in your mind here. But realistically, anytime we're talking about these collisions, if we talk about something, let's think about projectile motion, let's think about tossing the ball into the air. Why don't we say the speed is 0 at the bottom? Because there are forces acting on this. If we're looking at a before and after picture, let's imagine we have something that bounces a little bit. Not great, but bounces a little bit. Then we would expect to see, before it hits the ground, we would see a pretty big speed. After it hits the ground, it doesn't have as much speed. Right? And this is not just because of gravitational potential energy. This is because during that collision, there might have been some loss of that energy. Right? Some collision, vibration, heat, all of those good things. But at the end of the day, we can model this by thinking about what goes on with the force acting on the block. But now this is where it becomes a little bit difficult. Let's imagine a bouncy ball for a second. Let me draw out a flat line here. Jeez, let me scroll down for a minute first. Let's go ahead and look at this. Let me take a flat line. We're going to take, let's imagine a bouncy ball, right? Everybody has seen those rubber balls, sometimes called super balls or anything else like that. Let's even make it a fun color. Red's a fun color. Let's imagine this thing is hitting the ground. So at the first instant it's hitting the ground, it is still mostly circular. Maybe a millisecond later, we come back to this thing, and now it is deformed a little bit. Now it's looking a little bit more like this. Come back another millisecond later, and now we're at like our maximum compression. We've got something that looks like this. Then it starts to go back into its original shape from before. Not doing a very fantastic job of this, but I'm trying. Back up to a sphere. If we imagine the bouncy ball is kind of like a spring, right? That's not the most unrealistic thing in the world. There's, it's made of an elastic material. If we imagine this thing kind of like a spring, immediately we can already see the force is not going to be constant. The compression of that spring is changing in every step here. At every instance, the compression of the bouncy ball is a little bit different. So too will the force from the bouncy ball be a little bit different. And that's exactly what we're seeing in this graph right here. This graph right here is telling us that as this thing compresses, as it hits the ground, as it goes through that contact over a very short amount of time, but if we zoom in really close to that impact, we see that it is a time variable force. So the area under the curve for this Rather, when we sum up the entire thing, when we say, okay, well, the force is not constant, but if I take the integral of this force, if I look at the full change of momentum and I integrate this from where it first contacts to where it finally leaves the ground once again, I get what is called impulse. We write that as our capital letter J, also known as delta P, the change of momentum. And this too is a vector. Right, and that's an important thing. We're not looking at magnitudes here because this could be exactly what we see in this case, essentially a reversal of that momentum. The magnitude of the momentum going in could be the exact same as when it was coming out, but there was a change of momentum because the direction did change. Momentum is a vector. But this is what we would have to do with this. If we need to calculate out that change of momentum, we would need to see something like this. We would need to do some sort of derivative. Not a derivative, an integral, an antiderivative. So we might have to do this analytically, but of course, anytime we're starting to see complicated integrals, we generally speaking are going to look at this on a graph. So let's imagine this. Let's calculate out. Let's imagine we've got a 3 kilogram particle or a 3 kilogram bouncy ball that experiences the force shown below. Something just like this. What is the impulse, the change of momentum on the ball because of this time-varying force? Take the next, say, 3 minutes, and then let's take a look at this together. There is no quiz today. I didn't know how long discussion would take. I didn't want to try and risk it or anything else to have any sort of crunch to get through problems. Relaxing day today. No reading, no in class, none of that stuff. Units for impulse. Same as for momentum, being we've got mass times velocity. There's not a clean unit for all these things, so we just call it kilogram meters per second. Don't worry, there'll be stuff on Friday. I can dash those hopes immediately. Here, though. So let's go ahead and take a look at this real fast. So looking at this thing, we know it is the integral f dt. Right? If we were to find this impulse, I'm probably not going to write the capital J very often, for one, because I write weird J's. Capital J looks like this for me, and I've got a little bit of anxiety about writing my capital J's for some reason. But moreover, I don't think there's much worthwhile to have a special symbol when delta P, I think, does the job even better, because it is like, hey, that's the change of momentum, right? Like that fits better for me anyways. But generally speaking, this is always going to be f dt. And I want to leave this f with my vector symbol because, again, if momentum is a vector, so too should force be a vector, right? They're coming from the same place. But that means that I need to take essentially the area under this spot, the area this spot, the area this big spot, right? And all together here, this one here is going to be negative 500 times 1/2 negative 500 times the time that we do this. So that is 2 milliseconds, 0.002. That's the span that we would see from this one, is a negative 0.5, and then we've got two of them, right? So we've got a -1 coming from these two bottom sections, my top section here. I'd expect to be something as a 1 times 2,000 times now, as we're seeing this thing, this should be 0.006. That is the base of my triangle down here. Summed all up together like that, we get a +6 from this one. So we've got a 6 minus 0.5 minus 0.5. Our total change of momentum should be a positive 0.5 kilogram meters per second. Do we vibe with that one? All right. Something is just inherently funny to me, the idea that the vibe check is like somebody doing a check in hockey or something else where you just smash them into a wall. that image has not stopped being funny. I think about it every day for the last month or something. I think I saw one meme with it, and that's all that I've needed for all of this. All right, so let's imagine something else here. Let's, how did I find the 0.002? That is 2 milliseconds. Right, so I don't want to plug in the 2 necessarily. I want to keep this, all of my standard units are kilograms, meters, and seconds. So if this is in milliseconds, the first thing that I need to do is convert that back into seconds. Okay, let's check this one. Let's imagine we have a 200-gram ball, not kilogram, but gram, and we drop it from a height of 2 meters. It bounces on a hard floor and then rebounds to a height of 1.5 meters. Right, so the ground did eat up some of this energy. Of course, there was heat, there was vibration, there were sound, there were other things that were happening with this. That means that we don't get all of that energy back. So conservation of energy does not make it all the way through in the circumstance. However, assuming there's not that much air resistance, conservation of energy can still be very well used in this problem to help us find some of these values a little bit faster. So we're going to use a combination of conservation of energy and change of momentum coming from this graph. You know the general shape of this graph. You can find an expression for the impulse coming from this thing right here. But you don't know the exact value yet. You need to use your conservation of energy tools to figure out how much momentum needs to change to find that maximum force. So I'm going to say the next 3 or 4 minutes to work on this one. See what we can come up with for it. We will come back together and chat about it. All right. So let's start taking a look at this. So we know what the mass is. We know that there's initial height. We know that there's final height. We know that it falls to the ground in between those two things. This tells me about that change between the two. So let's draw this thing out first. Find ourselves a good space here. We have to imagine that it started somewhere up here, relative to the ground. At one point, it was on the ground, colliding with it. That is not in a particularly great place. Let's do it like that. There it is, on the ground, going through that graph that we just saw. And then finally, it comes up to this final height, y initial, y final, and we've got our collision graph right down here. Where it looks something just like this. Right, and this was a 5 millisecond time span. So very quick, not a very long time for that collision to actually take place. But what I need to do here is I need to actually figure out, this is supposed to be the change of my momentum. If I were to take the area inside of this, then what I really have is the change of momentum. So that change of momentum, as we would see it, this is supposed to be F max. And then we would say this would be 1/2 times F max, the height of our triangle times the base of our triangle, 0.005. So already we've got an expression right here that would tell us what F max was if only we knew what the change momentum would be. But we can see from what's going on right here, we can see what the change of momentum should be because we know something or another about the velocity of the object before and after in each case. Right, and we know that because this thing starts at a height. If it starts at a height and I drop it, it's going to fall, and I have an exact expression for how much energy it should have. So what I'm going to do is I'm going to say in our first circumstance, we've got a conservation of energy. M times G times Y naught should be equal to my 1/2 M, let's call it V1 squared. So my velocity right before I hit the ground, as I'm about to hit the ground. We don't need these masses here. That's totally fine. We can cancel those things out. We can, actually we do, well, let's just find the velocity first. Let's go with it in that order. There's a slightly tricky way to do this properly, but it's not worth it. Let's find the velocity first. That's probably the easiest approach here. That is to say, my velocity 1 should be equal to a square root of 2 times G times Y naught. Expression for V1, Can we extrapolate that we should expect the exact same thing for V2? Right? If I'm looking at this, I say, hey, now its kinetic energy turns into gravitational potential, but the equation's the same. 1/2 mv squared is equal to mgh. So, by that extension, the velocity v2 should be square root of 2 times g times y final. We've got our two velocities at this point. Take velocity 1, take velocity 2, just make those numbers. Make your life a little bit easier. Number, all of that good stuff together. Now what I'm going to say is that my change of momentum should be equal to mv2 minus or plus? What do we think? Minus because change, but here's a little bit of an issue that I just run into. We remember here, maybe we don't, but there was a discussion that I had with this of energy can make a lot of our old kinematics problems a little bit easier to solve. Realistically, it's oftentimes much easier to just write everything out in one big equation and have it there and ready to go from the beginning. However, it leads to a little bit of an issue because kinetic energy does not care about the direction. In fact, kinetic energy brushes right over it because it's velocity squared or speed squared. Whether it's going in the positive or negative direction, it doesn't matter. It's the same kinetic energy in either case, which is exactly why this expression right here works just the exact same way for our other circumstance, despite the fact that in our first circumstance, we could say that the velocity was negative, and in the second, the velocity was positive. The expression is identical because kinetic energy does not care. So I need to be a little bit smarter than that. I need to think, okay, it was falling down. This right here should have been a negative velocity. When I'm talking about a change like this, what I'm really doing is I'm talking about the change all the way to take away all of that negative and then add it all back as a positive. So for these quantities that I have only found the speed. If I want the actual velocities, what I need to say is that v1 vector is equal to negative v1 j hat. v2 vector is equal to positive v2 j hat. We need to be careful with this. We need to see what's going on in our picture and have a running description of what happens. Because again, momentum is a vector. Change of momentum is a vector, and we need to be careful with directions here. Energy didn't care. Momentum certainly does. So with that in mind, what I'm going to do is I'm going to say, we can say mv2 vector minus mv1 vector. I'm happy with that, because now that minus sign gets flipped around. Now these are just quantities. And I can say, well, this is all going in the positive j hat direction. Now we have our final expression. Plug all of those numbers in, move some things around a little bit, and what we should find at the end of the day here is that Fmax, if we want to just calculate this out as a number, that's totally fine by me. Fmax would be 2 times this delta P, divided by our delta t, which is our 0.005, our 1/2 associated with all of that stuff. That comes down to right here. That should be equal to 934.6 newtons. How does that feel? I mean, well, so realistically, if we just want to work it backwards from our final answer here, we should be expecting a change of momentum 934.6 divided by 2 times 0.005 should be something like 233. Why we add the mv2 and v1? Because if we are, so when we're talking about a change, so a change of momentum, let's talk about it like this. Let's watch my draw pad stop working. Hopefully it doesn't crash the rest of my system. Come on, there we go. change of momentum vector is equal to the essentially the final momentum vector minus the initial momentum vector. So that's exactly what we're seeing right here. Why we're adding this, though, is because we know at the beginning, as the ball falls down, V1 points downwards. In terms of vector components, it should be negative. What we found up here was only the speed. These are only speeds. We need to use our knowledge about kinematics to remember that, well, this should be pointing downwards, right? That's what I would have found if I had done this with kinematics. Energy does not care whether things are positive or negative. So we have to be looking at our picture and using a good description to make sure that we're following through with that. Does that make more sense? Pictures are still useful. That's one way to write this out. But pictures are still useful here. What we need to have is that velocity difference, but we are talking about these in terms of vectors. If I'm kind of reducing it down like this, when I plug in my vector, my V1 had a negative sign with it. The negative sign cancels out. I've got MV2 plus MV1. All of that was going in the Y direction. That's why I've got my J hat right here. And that is our quantity for the change of momentum. Change of momentum ended up being, if we actually crunched that number, 233.5 in the J hat direction. Okay. So let's move on for now. I've got one here. I don't know how well this is going to play, if it does or not. But this is kind of a fun one. If we can see this video, I imagine the frame rate is going to be terrible to the point that it's probably not going to work super well. I'm going to mute that as well because it's really obnoxious. Right? What a beautiful flip. Fantastic form. But let's imagine we're relaxing at the rec center. Again, context, this would have been, wonderful had the last year not happened. But aside from that, we have been studying for 10 hours straight, which this joke is suddenly not panning out super well at all. Let's just get to the point of the question. Let's imagine your friend asks you, when someone goes off a diving board, what is the force exerted on the diving board? Yeah, I'm realizing it's the joke doesn't come across very well right now. I recognize that. I think that the way this one had lined up, we had done this one right before exam 2 last time I did this, so it made a little bit more sense then. But anyways, we're wondering, what is the force exerted on the diving board? Isn't it just the weight of the diver? And there's kind of a difference here. You can see a little bit of a difference. If we go through this video one more time, what's going on there, you can see essentially as he walks out, there's a little bit of a slight dip in the diving board, but for the most part, it doesn't actually fall that far. Right? Again, imagine this kind of like a big spring. So the farther down it goes, the more spring force it's exerting. At the first point, you can imagine if you're just standing out there on the edge, of course, it is just the weight of the diver versus the weight of the board. Or the spring force of the board, I should say. Those two cancel each other out. But as we see, when he starts to jump up a little bit more, we'll just keep playing through this video, there's a slight dip and then a very, very intense dip the second time around. And that intense dip there, of course, as we know now, is because there is a very significant change in momentum. Before he was in collision with the board, he was moving downwards. The board had to change his momentum to send him back upwards and the other way. So the force exerted, of course, we know immediately must be greater than simply the weight, because not only is it holding him in place, but it's turning him around in direction, sending him back upwards. So I want to take what we've got in some of these numbers for this problem. Let's imagine the diver's about 60 kilograms. Let's imagine the first jump is a height of 1 meter. The second jump, as he jumps up, a height of 3 meters. Assume that it's kind of like a triangular force, right? Assume that it's a big old spring, and that's exactly what we would see as the compression goes. With all of those things together, I want you to, very much like last time, what is the maximum force exerted from the diving board? And how far does this force compare to the weight of the diver? Find it relative to just mg. So take the next, say, 4 minutes or so, and we'll take a look at this one together. So let's start taking a look here. Let's see what we've got. So, as I'm imagining this thing, we've got essentially 3 steps to this whole ordeal. For the sake of it, we're going to talk about essentially the height above the board at all states. For ease of drawing, let me just kind of separate this out into 3 separate things, like this. So we have state 1. Here's our person, what should be 1 meter above with a strange twist in his leg. We have state 2 standing on the board. Now at this point, we've got a variety of forces. Of course, there is a normal force from the board. Of course, there is gravity pulling downwards on our diver. And then finally, height of 3 meters, something like this. I'll call this initial height y initial. I'll call this final height y final. And then, of course, we've got these forces going on in the middle. So I can steal what we just talked about from last problem, and I can say, okay, well, I know that while I'm doing this thing, essentially the normal force is going to go like a triangle. If I'm looking at these things, we would draw this out something like this. I would compare force versus time. And I could even say that this is a normal force, right? Because what we're doing is we're coming in contact, the normal force increases because that's the springiness of the board is pushing back up against us through a normal force. So if you want to draw that out as a spring force or a normal force, either way is totally fine by me. Just recognize they're the same thing here. Got this. We've got this. Classic triangle, right? We see that in this problem, we're actually in contact for quite a bit of time. When we're actually looking at this, I'm going to guess here that second height takes the time profile is triangular. If we're actually looking at this thing, though, I'm going to take a wild guess. About 1 second. About 1 second is our total time in contact right here. So, and that's when we first see the feet touch the board, it goes down, it comes back up when the feet leave the board. That's actually about a 1 second time span. A lot, longer than what we have just seen in some of these other ones. But at the same time, when we're talking about a floor, I don't expect, it's not just, the floor doesn't move that much, realistically, right? The board is moving and bending to continue applying that force, so it's got a much longer contact time. It's also why you don't feel like a sudden jolt from the board. Because this impulse is spread out over a longer period of time, right? It's the difference if you're jumping from 1 meter or 3 meters or anything else down directly to the floor. Don't do that with straight knees, right? I feel like that is probably knowledge enough that you guys know, but the reason that you don't fall with straight knees is because if you do, then there's no bounce. If there's no bounce, then all of that force gets essentially shot straight down through your entire body all at once. You're going to injure yourself. Please do not try it. The reason that when you take a jump, you bend your knees when you fall is because when you bend your knees like that, now your legs don't have to provide this much impulse in the same time frame. They're allowed to do this over a longer time frame, and because of that, there is less force in one particular instant. There's less risk of injury. I don't trust anybody. Yeah, it is exactly like a crumple zone, right? Your knees are a crumple zone for when you jump. So, if we want to continue that analogy of if your knees are built different, like a 70s car or something else like that, before we created crumple zones, just realize that you're probably going to get a concussion, a neck or a back injury. We'll go with that one. That's probably the most apt. So, with all of that in mind, we're going to treat this problem just like we did last time. We have some initial height. We have some final height. We know that in the initial picture, we're moving downwards. We start at some height, we start moving downwards. We have some force on the diving board, we end up moving upwards. The combination of these two things together suggests to me that my initial velocity right here points, let's just say v1 negative j hat. We know it points in the negative direction. So if we can find that speed, we know it should be pointing negative, equals. If we find v2, we know this one should be positive. So let's do that. Let's say, all right, same deal as last time. All of my gravitational potential energy becomes kinetic. All of my kinetic energy becomes gravitational potential. In either case, though, I know the heights in both pictures. I'm after these speeds. Whoops, not why not, why final. All of those things together, looking at these comments, is he falling to the first picture? Yes. Falling to the first picture, because there's always like the multiple series of jumps. So we're looking at that last jump, goes up a little bit, 1 meter high, comes down onto the board, springs up all the way to 3 meters. We have two speeds. We can say that our change of momentum, please, I didn't even change windows. Ugh, every single time it does this. We can say that our change of momentum should be mv2 vector minus mv1 vector. However, we have already seen that our v1 vector is pointing downwards. It's a negative. So that means when we actually plug in these quantities, what we're actually looking at is mv2 plus mv1, all in the j hat direction. And one of the other ways that I rationalize this is that anytime I'm looking at changing the direction of my momentum, I know that my change should be greater than either individual momentum on its own. Right? Because one of these was going negative, one of them is going positive. To go back and forth between those two, I better be larger than either one of those. So that's just one little check that we've got to make sure that we're on the right track with all of our numbers. But we've got this. We also have that just in the exact same way, we know that impulse, change of momentum, would be the area under this curve right here. It is the integral f times dt. Easier found as an integral with just looking at this triangle. That is to say, this quantity right here should be equal to my, well, let's say f vector dt. If we want to just ignore these directions now, we have figured out what we need from what should be positive, what should be negative. Let's just go ahead and look at this as directionless at this point. v2, v1 is equal to 1/2 f max times our 1 second. When I put all of those numbers together, what I ended up finding was something like f max being equal to 1,451.4 newtons. Right around there. How does that actually compare to the weight? Well, m times g is only a measly 588 newtons. That means that in our final jump, the force the diver exerts on the board and the force the board exerts on the diver, F max is equal to about 2.47 times what just gravity would be normally. So quite a bit more, right? There's a significant increase in the amount of force felt, but again, kind of in the idea that when we are jumping on things, these are all supposed to be V. My difference between U and V is very slight when I'm drawing on a draw pad like this. My U's, I try to draw them like that. My V's are supposed to be drawn like that. But I do a very bad job with them. And then depending on which field of physics you're looking at, speed might be represented by U instead of V. So sorry to further complicate things with that. 588. This is just, that's the normal weight of the diver. That is just mass times gravity. That is the force of gravity on the diver. Because the idea here at the beginning was, isn't it just the weight of the diver? We say, no, not quite. It's not just the weight of the diver, because the force not only needs to cancel out gravity, it also needs to provide that upward change of momentum so that he jumps to the height of 3 meters as well. So when we're talking about that 2.47, that's where this comes from. We are 2.47 times this normal weight that we would feel from gravity. Yes, that is just part 2. You know, the fun part about this, it is kind of amazing to see some of these things. But so much of it, I love a lot of this stuff because you can just do this experimentally. A lot of the time, what goes into so many of these things is essentially we looked at things over and over and over and over again, and we tried to figure out, like, okay, so we keep seeing this thing. Is there an equation that we can come up with that talks about it? And, oof, ouch, multiple exams in a week. Oof, ouch, multiple exams in a week. But there's a lot of this stuff that is really cool. I mean, even to the point that you're doing all sorts of different things all over the place. You know, I get to see all sorts of these things, even when we're doing, you know, if you do any sort of research or anything else, you'll end up doing the same thing. Right now, it seems maybe like a little bit of a long shot, but, you know, you will get there and you'll go through these things and you'll see, okay, well, there are some equations that maybe we can use to start with this thing, and then we maybe narrow it down a little bit because we don't need this whole big equation. We can look at only the parts that really apply to us, and then before you know it, you've got, you know, your own derived equations for describing things. And just for everyone here, I'm gonna put an F in the chat for everyone with a bunch of exams. Again, I know that I've got a part in this, but I've got things that I need to do, courses that I need to teach, exams that I need to give out, kind of regardless, unfortunately. I feel for all of you, but I have my own part to do in this. But you will get through it. I am confident in all of you. I really am. And I'm not just saying that for anything else. I really do believe in every single one of you guys. But anyways, enough mopey nonsense. Let's go ahead and keep looking at some stuff here. So, we had talked, before I jump onto this next slide, you can already kind of see the title of it, but we had talked previously about there are quantities that become conserved in different situations, and if you have conserved quantities, then you can use those conservations to find other details. And we immediately applied that only to energy, but we didn't specify it was just energy. Momentum, as it turns out, is another one of those conservations. So immediately there's some problems with this. Conservation of momentum. Momentum is a conserved quantity. Sure. We just talked about the rate of change of momentum. Have I completely lost it? Have I immediately forgotten about what we just talked about in these equations in the last 3 problems that we all did where there was not a conservation of momentum? No, I haven't forgotten, but it's kind of just like the idea that work can be done to change the amount of energy. There are conditions for this conservation. If you look at the system of a whole, then of course some of these things might be conserved. There's different ways to look at them, but we can have conservation or we can have change. And we can use both of those as tools to help solve our problems. So when we're thinking about something like conservation of momentum, the condition here is that I have no external forces acting on my objects. As many objects as I might want to have, right? I could have 4 different objects, and I consider that my system. The momentum of these 4 different objects should be conserved. If they all collide with each other, that's okay. I'm going to call that an internal force. It is not a force acting on my system. It is forces acting within my system. Anything within the system, totally fine. Conservation momentum holds. Anything outside of the system. So imagine all 4 of these things were to experience gravity. If they all felt the force coming from gravity, conservation of momentum would not hold anymore because gravity is an external force acting on them. But as long as there are only collisions on the inside, that's totally fine. Momentum in the beginning should equal momentum at the end. If the net force is zero, then the momentum should be constant. So we have our big long list of how do we actually look at these things. How do we take a problem? How do we pick it apart? There's a lot of things that go into this now, right? Every day, our list gets a little bit longer. But not all of the steps apply. That is one of the nice things about this. Our list is getting longer, but we don't have to do them every single time. But we do have to keep track of which ones we have to do. And that is part of the challenge for this at this point. Right? This is where we start to grow on some of these things. It's not always just going to be an energy conservation problem. It's not always just going to be a dynamics problem. We might have some or all of these steps involved. And your job is to figure out which steps you need. So, as always, I would argue that these first three, every single problem, picture, reference frame, variables, they're in every problem, right? It is never a bad time to draw a picture. Even if one is provided, I do recommend at least drawing on that picture, if not drawing your own. I tried to, kind of in that same note, I know there was a little bit of discussion last time about some people would have liked more pictures from exam 1, so that was included. Probably not to enough degree, apparently, but other things on that one as well. We are trying to include more pictures for some of these problems. But drawing a picture, having a good picture, drawing on that picture, having a description. I'm grouping this in draw a picture plus description is kind of what I've got here. Right? Your picture is part of your description of what's happening. Define a reference frame, label the variables, then you have to think about, okay, what am I going to do? Is this a conservation problem? Is it energy? Is it momentum? Is it dynamics? You need to figure out which one of those it is. Break everything into components, if there are components to be broken up into. Do the physics, meaning write down the equations that you need, and then finally, do the math. Crunch the numbers, do the algebra. Let's try it. So previously, this problem has a little bit of a story behind it. Do the math, save the world, indeed. Previously, if you had taken this class with Dr. Alexander, this problem would have been a 1,500 kilogram car rolling towards your precious collection of porcelain babies. I don't have anything else on that. I don't know what to say. I don't know if he has a collection. I don't know what the context is behind that that's the way the problem is put in. I've changed it. You've got a precious collection of bongos. They've got a special place in physics, largely because if you follow this video down here, if anybody knows who Richard Feynman is, Richard Feynman was a very, very, very famous physicist. Really revolutionized how we teach physics, really revolutionized. He worked on the Manhattan Project. He was, a big name, to say the least. And the man was a freak. There's a video down there of him slamming on the bongos and singing about how he needs to drink his orange juice every morning. So, as such, we have themed the problem a little bit differently. You've got your grand collection of all of your bongos. You've got a 1,500 kilogram car rolling towards your precious collection. You can't possibly get to the car in time. So you decide, well, I've got all of these 10 kilogram blobs of clay in my backpack. I haven't pitched in a long time, but perhaps we can just get this. Blobs of goo, indeed. Yeah, that's the way to do this. Much better. That's a great improvement. You carry these around, I assume, for artistic purposes. How fast do you have to throw this blob of goo to stop the car? I mean, at this point, I'm pretty sure your backpack is only, with 10 kilograms of goo, I'm pretty sure that's the only thing in your backpack at this point. Forget books, notebooks, pencils, pens, laptop. No, just goo. You open up the entire thing and it's just goo. But let's take the next 2 or 3 minutes. Conservation of momentum is the key here. See if you can come up with a good answer. All right, I want to start to take a look at this one. So let's imagine we have car. Yeah. Moving at some sort of velocity. So let's say V of C, M of C. It's going this way, right? So the momentum of this car is pointing to the right. Momentum, car, going this way. The goo, on the other hand, green's a good goo color, hurtling towards it at some unimaginable speed for as fast as the thing needs to go. Call it V of G. The velocity of the goo going like this, the mass of the goo, the momentum should be going like this. Not M. We use P for momentum because it's a silent P, you know. Right? Like all of those other things that have a silent P at the beginning of the word for some reason. So this is a circumstance of momentum conservation. And we're about to hit this in a little bit more detail here. But if there are no other forces, if nobody has a wind tunnel or anything else blowing on what's going on here, then the momentum that we start with, P initial, should be 0. If we want our final momentum to also be 0, right? The car has stopped, is 0 momentum. That's what we're shooting for. So we have to say, well, then our momentum in the initial picture must also be 0 to make that happen. So then, what that's saying is that what we should have is something along the order of the momentum of the car minus the momentum of the goo should equal 0. If these two things are equal, we have the mass of the car, we have the mass of the goo, we have the velocity of the car. We need to find the velocity of the goo. Put all together like this. Velocity of goo should be something along the order of the momentum of the car divided by the mass of the goo. This is how fast we would have to throw this goo to actually make it stick, and that is 300 meters per second. For context here, this is about 671 miles per hour. Are you feeling lucky? Set both of the momentums equal to each other as long as you're talking about quantity rather than the direction as well. In this equation right here, what I've got is the direction kind of included within that. Right, I've got the minus sign here because technically the momentum of the goo is pointing in the negative x direction. If we're talking about speed, 300 should be the answer because speed, again, will never be a negative quantity. But if you had negative 300 for the velocity, I'd be totally fine with that. Realistically, like, I'm not going to split hairs too carefully on that one. But, you know, it's just to be very careful. I'm not going to split hairs too much on that one, but if we are trying to be proper, then we would want to say that our speed is 300. MV minus MV, this is my momentum when I start. So this is my initial momentum versus my final momentum. should be 0. If everything is stopped, then we have a final momentum of 0. But my initial momentum, the car is going to the right. The goo is going to the left. That's why we've got a plus on the first one, a minus on the second. But again, it's kind of the circumstance. If you find a negative or a positive value or anything else, if you've got the right value, you can talk about what it actually means. Even if you come up with an extra minus sign or something else, as long as you've got a good description of why you're like, okay, well, it's minus because this reason, but I know it's actually this, right? That's totally fine by me. That's exactly what I love to do all the time. I'm a physicist. I'm not a mathematician, right? That's why I did not do so well in the math major, because I like to wave my hands around and say, well, I know it should be this because I've got this description, because I've got this understanding of the problem already. And I'm not a big fan of the G sus4 chord. Not a fun one to play. Doesn't sound very great. Okay, so all of this, right? This is actually our first experience with what's going on right here. All about sticking together. So there are different types of collisions. There's a small variety of collisions that we can have, but the first one that we're going to talk about here is what we call a perfectly inelastic collision. Perfectly inelastic collisions mean that two objects that collide stick together and move together. They collide and they form into one object that is now moving together all at once. So this is a perfect example of this happening if we have the clay ball, if we have the goo in the car. In either of these scenarios, what we're expecting here is that it collides with our other object and they stick together. And that's what they're doing from now on. There are other types of collisions that might see things bouncing off or anything else like this, but when we're talking about two objects, when they stick together, that is a perfectly inelastic. And that also means that momentum is completely conserved as well. So, with no external forces, I mean, we expect that, right? With no external forces acting on these objects or anything else, we don't expect the momentum to be any different. So the momentum of the two objects together should equal the momentum of the final object as it decides to move. We can do this in one axis like this, or we could perhaps have it happening in multiple axes. The last problem on this one, I'm not going to make you guys solve something else. Let me just do this one as an example, because we just saw what to do with this one. You guys worked this one out. What we can imagine here, I've got a 10-gram ball of red clay traveling east at 2 meters per second. I'm just going to run through this one. We're towards the end of the day here. We've got this thing coming in like this, traveling east. We have a blue piece of clay traveling 30 degrees southwest. What did I do with this one? Did I make this more complicated for no particular reason? Yeah, I did. Ugh, every single time. Let's get rid of that thing for now. Let me redraw this in a little bit of a better spot. Let me just do this one so we're having a little bit of an easier time, because again, I know you guys do have exams and everything else going on right now. So let's label that 30 degrees, going down like that. I'm going to go ahead and label my axes, because that's, of course, always important to do. Y and X, we'll call them just like this. So what I can do with this is I can say, okay, well, these two are going to slam into each other. They are going to combine into, we'll do like a violet piece here. They mix together into something, they'll probably fly off like this. Call it V final. So when I'm looking at these different momentums, I'm going to call this V of the red. I'm going to call this V of the blue. We know the masses. We know the velocities. We know all of these details that we could have here. So if I am to write out my initial versus final momentum, let's do it like this. Initially, what did we have? Well, I had my red clay moving in the X direction only. So let's do this in two separate pieces. Let's start by saying in the X direction, what do we see? Mass of the red times the speed of the red, going in the positive X direction, so there's no minus sign or anything else like that. On the other hand, the blue blob of clay is going to be going with something like MBVB cosine of theta. Let me move this over a little bit more. Right, cosine of theta, because I imagine if it goes into 0, then it would be pointing only in the x direction. All of that stuff together, summed up to give us some sort of final momentum, should end somewhere like this. The mass of the purple blob times the x component of my final velocity. I'll just call it Vx for now. So if I do that, I can crunch that number and I can say that Vx should be equal to 0.28 meters per second. I'm going to do the exact same thing with the y direction now. I'm going to look at the y direction and I say, wow, good job, red blob. You really helped. I look at the blue blob and I say, okay, well now this is minus mb v of b sine of theta should be equal to the momentum in the y direction of my purple blob. That is m of the purple blob times v in the y direction. Sorry, and I should contextualize here. The mass of the purple blob is the combined masses of each of these together. That's why we've drawn it as purple, because it's the red plus the blue, slammed in together at this point. They have stuck together. So with all of that in mind, we find that our velocity in the y direction is a negative 0.3 meters per second. That means for a total speed as we would have it, I guess this goes without saying that we should have the I hat and the J hat there for those things, right? Because I'm talking negative, positive velocities. If we're looking for the final speed, though, I'm going to take, of course, just our typical Pythagorean theorem. Vx squared plus Vy squared should equal a total of 0.41 meters per second. How are we feeling on that? Goo. All right, team. So again, this goes for not just necessarily things in regards to this slide, this exam, or anything else like that. Please don't hesitate to open up lines of communication with me. Like, really, I don't know what else to say towards that one or anything else. I really am more than happy to always take questions, chat with you guys, anything else that you have coming up like that. Like, don't hesitate to reach out to me about anything. I really am always happy to chat. And if I don't respond within a couple hours or something else like that, send me a gentle reminder email. I might be thinking of a response, or perhaps I'm just busy with something at the time. On the rare occasion that I've forgotten, that will help make sure that I don't miss that. But please don't hesitate to talk to me about things as they come on, or anything else like that. Good luck with the rest of your exams. I know this is one hell of a couple weeks. So, yeah, all that good stuff. Let me know if there's anything I can help with. Let me know if there's anything that we can chat about. And I'll see everyone again next time.